Okay, so for this question, we're given g of x is equal to this function over here, where x is bigger than 3. And then we're trying to show that it can be rewritten as this x plus 1 over x minus 2, where again, x is bigger than 3. So that first part's pretty straightforward. It's just a bit of algebraic manipulation with what we have over here. In part B and C, it gets harder. Right, so part A. I'll just rewrite what we have for g of x. So to simplify this, we want to combine these two fractions together, and we can do so by first factorizing this quadratic over here. So to factorize that quadratic, we're looking for two numbers that times to give minus 6 and add to give plus 1. Those are 3 and minus 2. So that quadratic can be factorized as x plus 3, x minus 2. So I'll just rewrite that. And notice how both of these two denominators, they share a factor of x plus 3. So then to make a common denominator, we just have to times top and bottom of this fraction by x minus 2, and then both fractions will have the exact same denominator. So then our shared denominator would then be x plus 3 times x minus 2. If we multiply top and bottom of this by x plus 2, the top will become x multiplied by x minus 2. This stays as is, 3 times 2x plus 1. And now we have one single fraction. So now we can simplify this. So multiply it all out, we get x squared minus 2x plus 6x plus 3, all divided by, I'll keep it factorized, so x plus 3, x minus 2. The numerator simplifies, so just bring these two terms together. They become 4x. And then we can factorize the numerator. So two numbers that times to give 3 and add to give plus 4 are 3 and 1. So the numerator factorizes to make this. The x plus 3's cancel, and then we are left with x plus 1 over x minus 2. The domain was x is bigger than 3. That has not changed, so it'll still be x is bigger than 3. And now for part B, find the range of g. So there's a few ways in which we can do this. I think the most foolproof way of doing this is to know what this graph of x plus 1 over x minus 2 looks like. And there's a couple of ways in which we can do this. So this here is a transformation of a 1 over x graph. But to understand what that transformation is, to know what that transformation is, we have to first manipulate this function. So there's a couple of ways of doing that. The first method that we can use to do this is long division. So that's probably the most intuitive way of doing this, but there is a nicer way of doing it, which I'll show you afterwards as well. Okay, so long division, we're doing x plus 1 divided by x minus 2. We see how many times the x goes into this x, that is once. We then do the 1 multiplied by the x minus 2, that gives us x minus 2. Subtract the two things, that gives us 3. And that means that x plus 1 over x minus 2 is equal to the quotient 1 plus the remainder 3 over the divisor x minus 2. And if you're not sure why it's written in this way, consider 7 over 3. 7 over 3 is the same thing as 2 and a third. And 2 and a third is the same thing as 2 plus 1 over 3. So you know that 3 goes into the 7 2 times, you know there's a remainder of 1, and then this 3, this divisor you just put over there. And again, it's the same thing as 2 plus a third. Notice the similarities between what we have over here and what we have over here. So the 2 in this scenario is the quotient. It's the number of times 3 wholly goes into 7. In this example, that was the 1. So the x minus 2 goes into x plus 1 once. Then we have plus our remainder. Here is our remainder in the left-hand side example. And then we have our divisor on the bottom. Our divisor in this example was x minus 2, which is what we have over here. So if you're not sure which way these three things go, just think of this example, and that will help you to remember it. Okay, so this here is the form that we want our fraction to be in to know what the transformations to the 1 over x graph are. I'll just quickly show you another way that you can go from here to here. Okay, so here's our fraction. What we're trying to do is rewrite the numerator as something involving x minus 2. So basically we want to have an x minus 2 in the numerator. Well, obviously x minus 2 is not equal to x plus 1. How can we make this equal to x plus 1? Well, we can just simply add 3. Minus 2 plus 3 is plus 1. So this is all divided by x minus 2. This is no different to what we have over here, but why is this better? Because we can then write this as x minus 2 over x minus 2 plus 3 over x minus 2, which is then 1 plus 3 over x minus 2. This fraction over here just gives us 1. So it's the exact same thing as what we have over here. So both methods are fine. You can do either one, whatever works better for you. I personally prefer the second way of doing it, but again, either way is fine. So now we have 1 plus 3 over x minus 2, and we can use this to work out the transformations that have happened to a 1 over x graph to give us this function of x plus 1 over x minus 2. So just bringing it back to the question, so you know what we're doing, we're trying to find the range of g of x, we're trying to find the y values, the output y values of this function, so knowing what it looks like is a nice foolproof way of figuring out what that range should be. So we have a 1 over x graph which looks like this. Now if this 1 over x graph turns into 1 over x minus 2, so that minus 2 is being applied to the x, that's a translation of 2 to the right. So then the graph would look like this. So this asymptote here is x is equal to 2. The whole thing has shifted to the right. Then we have the 3. So we're timesing the fraction by 3. If we multiply the entire fraction by 3, that's affecting the y-coordinates. So basically everything just gets steeper. All the y-coordinates just get multiplied by 3. The graph pretty much looks the same, just a little bit steeper. And then the final transformation is the plus 1. So we're adding 1 to the entire fraction. And if we add 1 to the entire fraction, then what it does is it shifts the entire graph up one place. So previously, the horizontal asymptote was the x-axis. Now that asymptote has gone up to y is equal to 1. So there's an asymptote here, that's y is equal to 1. We still have the same asymptote of x is equal to 2, that hasn't changed. We haven't done anything that affects the x-coordinates with this plus 1. And now our graph looks something like this. I'm not sure if this part of the curve is above or below that point. We don't need to worry about that. And the reason we don't need to worry about that is because going up to the original function, we're told that x is bigger than 3. That's our domain. So going back to this, if this is x is equal to 2, then the part of the graph that we're considering is just this bit over here, from 3 onwards, from x is equal to 3 onwards. So I'll just draw that a little bit neater over here. Okay, so here is our graph again, just drawn a little bit neater, a little bit bigger. Again, this asymptote is y is equal to 1, and this function is our g of x. And x is equal to 3 is, let's say, over here. So this is 3. If the domain of our function is x is bigger than 3, that means we're considering all points to the right of this. So what is the y-coordinate for this point? Well, g of x is equal to x plus 1 over x minus 2. And then so if we put in 3 into this, 3 plus 1 over 3 minus 2 is 4 over 1, so 4. So this point, or the y-coordinate of this point over here, is 4. Okay, so the range. The range is the y values. We're starting here, the y value is 4, or actually we're starting just after that point. So we start with a y value just underneath 4, or just less than 4. And then we go all the way to the curve approaches y is equal to 1, but it never reaches it. So therefore our range would be 1 to 4, not inclusive. So g of x is between 1 and 4. Doesn't equal either, because this curve will never hit the asymptote, and this point is not included in our function because x has to be bigger than 3. Therefore g of x is less than 4. And that's our answer to part B. And then finally for part C. Find the exact value of a for which g of a is equal to the inverse of g of a. Okay, so there is a quick way to do this. What I'd imagine most students would do is they would find the inverse of g of x and then set that equal to g of x itself, and then from that work out the solution, so work out what a would be. But you actually don't need to work out the inverse function. There is a quicker way of doing this, which I'll show you. Okay, so I'll just write out the function. Alright, so here is our function. So what I will do is, I will consider some random function. Let's just say like, we have a curve that looks something like this. Let's call this curve f of x. I'll then draw the line y is equal to x on this graph, so that's this. So, if we have a function y is equal to f of x, if we find the inverse of that function, it'll be a reflection of this curve over here in the line y is equal to x. So that would look something like this. So this would be the inverse function of f of x. Okay, so if we wanted to work out where the original function f of x and the inverse of f of x meet, we can just set those two things equal to each other. We can solve them simultaneously, set f of x equal to the inverse function, and then work out what x is. But notice how they also cross the line y is equal to x at the point where the two curves intersect. So a quicker way of working out this point of intersection would be to not solve these two equations, f of x and inverse f of x, simultaneously, but rather to solve one of these two equations simultaneously with y is equal to x. So we can solve this equation, the y is equal to f of x, with this simultaneously, and that will give you this point, or we can solve these two equations here simultaneously, that will also give you this point. So we can do the same thing here. With our g of x function that we have over here, we can solve that simultaneously with y is equal to x. So from the function that we have over here, y is equal to that. So y is equal to x plus 1 over x minus 2. We solve these two things simultaneously. So x plus 1 over x minus 2 is equal to x. And then we can just solve this equation here. So bring the x minus 2 to the right, times it. Let's multiply that out, so we get x squared minus 2x. Bring everything to the right, we get x squared minus 3x minus 1. And if we type this into the calculator, we get 3 plus or minus root 13 all over 2. So we have two solutions. Are they both valid? Well, remember that we know that x has to be bigger than 3. So if you were to look at these two numbers in your calculator, 3 plus root 13 over 2 and 3 minus root 13 over 2, the minus 1 will be less than 3. So it's just the positive one that we're considering here. So that will be our solution for a. A being the solution for g of x is equal to inverse g of x. A is that number. So a is equal to 3 plus root 13 all over